fun lesson today. Sorry I couldn't be here, but you know, I had important things to do, so I didn't want you to miss out on your learning opportunities. So today what we are going to talk about is more trig identities. So these ones are really important. They're going to come up all the time. All the time. And when I say all the time, I mean all the time, like your unit circle comes up all the time. So let's think about this. Go back in time to the days of your unit circle. And what do we know about your unit circle? Well, it's a circle with a radius of 1, right? And any point on this graph can be called some point x, y. And because I know this is the equation of a circle, remember, I can say, oh, that's just equal to x squared plus y squared is equal to 1. Basic, you learned that a long time ago. But remember when we were talking about the unit circle, the x and the y really had more special meaning. Whereas the x values were really equal to the cosine of the theta, whatever angle theta you're talking about. And the y values were really equal to the sine of theta. So if we take this x is really the same as cosine, and this y is really the same as sine, and we substitute it back into this equation that we've been working with for years, we see something very special. That cosine squared theta plus sine squared theta is really just equal to 1. Oh my gosh. Oh my gosh, I hope you can remember that. So let's think about how that works. Let's try one. Maybe you're sitting there going, I don't believe you, Ms. Kreppel. You're crazy. It can't be that easy. Let's try one. Let's say that theta is equal to pi over 6. And then I want to find the cosine of pi over 6. And then I'm going to square that. And I'm going to add it to the sine of pi over 6, which I'm also going to square. And hopefully, if I do everything correctly, it's going to turn out and end up being 1. So let's see, cosine of pi over 6, root 3 over 2. So I'll have to square that. Plus the sine of pi over 6, oh, let's see, 1/2. I'm going to square that whole thing. So let's see, root 3 squared is 3 over 4, plus 1 over 4. Oh my gosh, look at that, common denominators already. All I have to do is add the top, 4 over 4, which is really equal to 1. Ta-da! So, this identity is going to work all the time. As long as you substitute in the same angle here, it'll be true every single time. So as long as these two things match, you're fine. So I could have the cosine squared of 8,000x plus the sine squared of 8,000x. And because these two things are the same, these two angles are the same, and you're squaring the sine and the cosine, it doesn't matter what it is, it's always going to be equal to 1 every single time. Okay? It doesn't matter what all this junk is inside here. Okay, so that leads us to start talking about more fun stuff with these identities. So these identities have a special name, and they are called the Pythagorean Identities. Okay, so they're called the Pythagorean Identities because they're based on the right triangle situation here, x and y. So x squared plus y squared equals 1. Oh my gosh, oh yeah, there's the Pythagorean theorem again, unit circle again. So the most basic one we know is that sine squared theta plus cosine squared theta is equal to 1. That's the best one. That's the basis of everything. And then what we can do is think about having some fun with our other trig identities that we were talking about on Wednesday. And if I divide all of these things by sine squared theta, sine squared theta, I get 1. Let's see, cosine theta over sine theta, that's just cotangent squared theta. is equal to 1 over sine, let's see, that's cosecant, so that's cosecant squared theta. So here's another Pythagorean identity that we can use. Oh my gosh, look at that. 1 plus cotangent squared equals cosecant squared. Now I know a lot of you guys are saying, you can't just divide everything by sine, and I can because it's an equation. So as long as I divide everything by the same thing, it's fine. And I hear all you guys out there in the audience saying, oh, how sad, you divided everything by sine squared, but what about cosine squared? Okay, let's see what happens if we do that. So I get sine squared theta, I'm going to start off with the same thing, plus cosine squared theta equals 1, and I'm going to divide all of these things by cosine squared theta. Divided by cosine squared theta, divided by cosine squared theta. Oh my gosh, sine over cosine, so that's tangent squared theta plus 1 is equal to secant squared theta. Dun dun dun, dun dun. So we have 1, 2, 3 Pythagorean identities that you guys have to memorize. Now I'll tell you a little secret. I have this one memorized, and I always have to go through the process of doing all the dividing each time to remember the order. Like I know cotangent and cosecant goes together, but I can't remember like where the 1 comes in. So it doesn't take me very long to just do this on my work papers. Like if I do sine plus cosine equals 1, and then I'll just divide everything by sine, and then I'll be like, oh yeah, that's 1 plus cotangent squared equals cosecant squared, or secant squared. So, let's see. Let's try an example. So the other thing that you have to do is realize that because these are equations, you can always manipulate them. So I could move this cosine to the other side and say, oh, it's really the same thing as sine squared theta is equal to 1 minus cosine squared theta. Or I could do the same thing with the sine squared and say, oh, cosine squared theta is equal to 1 minus sine squared theta. Something like that. So I'm sure you guys understand properties of like adding and subtracting things to both sides. So just keep in mind that you can do that for all of these. Subtract things from both sides. Isolate what you want. Let's do a couple examples. Oh, this is fun. I wish I was here to share this moment with you. Okay, so I'm going to do this one. 1 plus cotangent squared x divided by secant squared x. So let's see. 1 plus cotangent squared x. I have that right over here. 1 plus cotangent squared theta. Does it matter what the variable is? No. But I know that that whole thing on the top then is going to be equal to cosecant squared. So that's going to be my next step. Just write cosecant squared theta, or x in this case, over secant squared x. Now when I have things written like this, a lot of times things will cancel out and this will end up being like a tangent or a cotangent because I know that this is really the sines and cosines. So I'm going to rewrite this in terms of sines and cosines and see if I can simplify it at all. So that's really the same thing as 1 over sine squared x divided by 1 over cosine squared x. Oh, so I have a fraction and then another fraction and I'm dividing them, so that's really multiplying by the reciprocal. So 1 over sine squared times the reciprocal of the bottom. Oh, so look at that, I just get cosine squared over sine squared, which is just equal to cotangent squared x. So all of this stuff that I had here at the very beginning, dun 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 dun, is really just equal to this. That's a lot easier to think about it like that, huh? I would much rather just write cotangent squared than all of this stuff. Ew. Okay, so let's try another one. I hope you guys wrote those down. So 1 minus sine squared theta over cosine squared theta. squared plus cosine squared is equal to 1. Here's how I do it short. So if I subtract sine squared from both sides, then I get cosine squared is equal to 1 minus sine squared. So this whole thing on the top is really just equal to the cosine squared of theta divided by the cosine of theta. Oh my gosh. And then if I have something squared over something linear, this is going to cancel out the squared, so I just get cosine theta. Okay, that's not so bad. So the more basic ones is just going to have you simplify, and that's not going to be too strenuous of a task. As long as you remember your identities, sine squared plus cosine squared equals 1, right? 1 plus cotangent squared equals cosecant squared. And then tangent squared plus 1 equals secant squared. So let's try an example that might be a little bit harder. So I think I have one over here. 1 over sine squared x plus secant squared x over tangent squared x. Oh my gosh, oh my gosh. Okay, so here's the reason why some people start freaking out over identities. I know I'm not talking about anyone in here. You guys are going to be fine. It's the fractions. Because anytime you add fractions, still in trig, just like in 3rd grade, what do you always have to have? Yes, you're right. Common denominators every single time. So what I like to do with problems like this is I look at this and I say, okay, I have 2 fractions. I need to add them together. The denominators need to be the same. So right now this one's sine and this one's tangent and this one's secant. And I know that I can't simplify this one any further because sine that's as simplified as you can get when you have sines and cosines. So what I'm going to do with this over here is I'm going to try to rewrite this all in terms of sines and cosines and see if something cancels out. So I'm going to write it as 1 over sine squared x plus secant squared, which is 1 over cosine squared x, divided by tangent squared, which is 1, oh, that's not right, oh my gosh, sine squared x over cosine squared x. Okay, so wow, if I just take a look at this piece right here, and I'm going to multiply by the reciprocal of the denominator. So let's see, I have 1 over cosine squared x times cosine squared x over sine squared x. What's going to cancel out there are the cosines. So I can rewrite this whole thing as 1 over sine squared x plus, oh my gosh, 1 over sine squared x. Look at that. Now, the great part here is I have made common denominators. So when I have a common denominator, all I do is I just add the top. So 1 plus 1 is 2. So I get 2 over sine squared x. So you could leave it like that, or I could also write it as 2 cosecant squared x. Well, that was a nice one. I didn't even have to use any identities, any of the Pythagorean identities. Wow, cool. Okay, let's try another one. Secant theta divided by sine theta minus sine theta divided by cosine theta. Oh my gosh. I always take a look at these and think I'm so unfortunate because I don't have common denominators. And then I think, oh, I can't be upset about that because I know how to fix things. I can just make them common denominators and then my life will be great once again. So, what you need to keep in mind on all of these identity problems is that they're not equations, they're just expressions that we're trying to simplify. So I can't like multiply the whole thing by something because I don't have it equal to anything. So I just have to use all the properties that I'm comfortable with, which are just basically turn everything into sine and cosine and get common denominators. So 1 over secant theta is really equal to 1 over cosine theta. And then 1 over cosine, or a secant in the top, is really just the same as if I write it like this. Cos theta sine theta minus sine theta over cosine theta. Okay, now I feel like we're getting somewhere. Because here, this has a cosine and a sine, and this one just has a cosine. So I have to get a common denominator. So what do I need to multiply this side by to get it to look exactly like the bottom part here? That's right, a sine theta. Okay, good, you're getting it. I'm impressed. Okay, so sine theta over sine theta. Oh my gosh. I see what's going to happen here. This is exciting. So let's see. I have a 1 minus a sine times a sine is sine squared. 1 minus sine squared theta over the sine of theta times the cosine of theta. And then remember from our Pythagorean identities that 1 minus sine squared, that was equal to cosine squared theta over sine theta times cosine theta. Now that I've turned everything into multiplication, simplifying is a breeze. So this cosine in the bottom cancels this one out of the top, and I'm just left with cosine theta over sine theta, which is just really equal to cotangent theta. Well, these are fun. You guys are going to get a chance to practice with your friends in a second. Okay, I'm just going to do 2 more examples for you. And they're easy because you already know how to do it. Well, first of all, I'm going to do... recall, this doesn't really count as an example because I'm just refreshing your memory. If I have something like x squared plus 5x minus 6, and what you're going to have to do with this is factor it. So you're looking for 2 numbers that multiply together to be -6 and add together to be 5. And so that's 6 and -1. So you factor it like this. Right? That's not so bad. Well, what happens instead of if I have just x's here, if I have trig functions here? Of course we're going to put sines and cosines in there. So let's see. I'm going to get, let's say I have this, cosine squared x plus 5 cosine x minus 6. Well, this is exactly the same problem as that, except instead of the x's, I have cosines. So instead of these x's here, all I do is replace them with the cosine. So I'm going to do cosine x plus 6 times cosine x minus, 1. And you factored it. Okay, that's not so bad. That's something you already know. So let's make one that's a little bit more complicated. This is the last example. I promise you. Thank you for bearing with me. I know that this is not the most exciting. Oh, I know. Okay. You guys are too kind. Okay, plus 1. Now, over here when we did this example, see how we had everything all in the same trig function? So that is the best case scenario when you have that. Over here, I have cosine and sines. Not the best case scenario. So what I have to do is do a substitution to get all matching functions. Okay, so let's see. Cosine x, that's as basic as it can get. So I can't substitute anything for this. So I'm just going to rewrite that as cosine x. because that's as basic as I can go. Now here, sine squared, anytime I have something squared, I can substitute in my Pythagorean identities. So I'm going to do the same thing, minus 2, and sine squared is really the same thing as 1 minus cosine squared x plus 1. Oh, now look at that, I have all cosine functions. So I'm going to distribute through the negative 2, so I get cosine x minus 2 plus 2 cosine squared x plus 1. And then I'm going to rewrite that as 2 cosine squared x minus cosine x minus 1. Plus cosine x. So I combine like terms. Alright, so now I have a 2 cosine x out in the front and a cosine x right here. And then these two numbers at the end have to multiply to 1. So I know that these two have to multiply to 2, so that's the only way I can do it. And these two have to multiply to 1. So now the only thing I have to do is make sure that when I combine the terms, that the middle term is positive. So that means that this one has to be attached to the positive one, and that's the negative one. Fun! Okay, so your assignment is on the board over there. And then you guys can get started on that. And then next week, on Monday, we're going to be solving things like this. So have fun. I'll see you Monday. Bye.